talking of an n-type semiconductor, n subscript n refers to the majority carrier in an n-type semiconductor, and correspondingly p subscript n refers to the minority carrier.
So if you use a starting in the P.
Sure, no problem. Okay, what I would like to do is to talk about majority carriers and minority carriers briefly today by way of review. We will see the notation that we used. And as I am saying, n subscript n is for the majority carrier, p subscript n is for the minority carriers in an n-type semiconductor. And correspondingly, the symbols are the opposite. P subscript p for a majority carrier, and n subscript p in a p-type semiconductor. And we noted that these are what are the instantaneous values at any given instant. Accordingly, we also introduced the equilibrium notation n subscript n naught, or p subscript n naught as the equilibrium values. And sticking to an n-type semiconductor, we noted that this product is equal to Ni squared, which was known as the law of mass action. And then we also had the notation of the instantaneous, of the change in the carrier concentrations. For example, when we illuminate the semiconductor with a light that is sufficiently strong as to cause excitation across the band gap. So all of a sudden we've got extra electrons and holes that are created in equal numbers, EHPs, as we refer to them. And what I ended up pointing out the last time was that there is a very drastic change in the carrier concentration that takes place as a consequence of this illumination or injection of carriers. I will just briefly go back to it. We saw that, say, for example, in a particular example that we saw, if the initial values were for the equilibrium, say 4.5 into 10 to the power 3, I'm not going to go through it all, but just by way of a quick review. We have n subscript n naught, and then we had Ni. We took an example like this and we looked at it. This is, of course, on a log scale, 10 to the power 10. This is before illumination, and after illumination we saw that there's a drastic jump from this value to somewhere around here for the P, for the whole concentration as a result of the illumination, where it now comes to be about 0.5 into 10 to the power 16. Meanwhile, the electron concentration has gone up to about 5.5 into 10 to the power 16. The earlier value was somewhere here. So we've changed the electron concentration only marginally by illuminating in an n-type semiconductor, but the whole concentration has changed by about 10 orders of magnitude. Not 10, more than that, 15, 12 orders of magnitude. So that's what we had looked at last time. So this is the effect of the illumination is such as to increase the whole concentration drastically. Now when it comes back into equilibrium, when we stop the light, what's going to happen? These things have to recombine to establish these two equilibrium values again. So all these holes have to go somewhere. So this extra number of holes that were created are going to recombine with the extra electrons that were created. But it's going to take some time, and in that context I introduced the idea of minority carrier lifetime. As the average time that the hole, which is the minority carrier in this case, would remain free before it recombines with an electron after the illumination has been stopped. So now it will recombine in some lifetime which we will refer to as tau h, and within that time it will recombine. And then we said that 1 by tau h is then correspondingly the probability, the average probability per unit time that a hole will recombine. The inverse of the lifetime. And I'd kind of left us with that idea there. once the hole is trapped somewhere, then there's plenty of majority carriers available. So the factor that determines this lifetime is how many what are the recombination centers available, the concentration of that, because then the hole will get trapped there, and there's plenty of majority carriers with which it can easily recombine. So the defect structure of a material, which is related to the recombination centers, is then a factor that decides what will be the minority carrier lifetime. If we have a lot of defects, and particularly electrically active defects, then that could influence the lifetime severely. And I left this somewhere around there. And I want to take that up further now. Let's take an idea that we have, let's say, created delta Pn of, say, 1,000 holes by illumination, just to take a concrete example. And the lifetime of these holes, the minority carrier lifetime, is about 10 seconds, average lifetime for these. So what that tells us is that the rate at which they are recombining will be given by about 100 per second. They have a lifetime of 10 seconds, and there are 1,000 of them. So on average, about 100 per second are recombining. So this rate here, delta Pn by tau h, is the recombination rate of the minority carriers. Okay? Don't worry about the exact numbers, but I just want to point out it's delta Pn by tau h. So summarizing these ideas a little briefly, the rate of increase of minority carriers namely delta Pn is equal to, d delta Pn by dt, the rate of change, is equal to the recombination rate, the rate of generation, how many are being generated per unit time, minus the rate of recombination. And we just saw that the rate of recombination is given to us by delta Pn by tau h. So if we write the rate of generation, which is related to how strong that illumination is and so on, as Gph, then we will get that d delta Pn by dt is equal to Gph minus delta Pn by tau h. So if this is 0, if it's steady state, that means the rate of generation will be equal to the rate of recombination. Now in certain cases we want tau h, the minority carrier lifetime, to be small. In other cases we would like it to be large. For example, when tau h is small, that is or short minority carrier lifetime, that is an advantage for fast switching of p-n junctions. Okay? We want short minority carrier lifetimes. On the other hand, when you're dealing with optoelectronics, where we are interested in the emission of light, then the minority carrier lifetimes, we want them to be longer. Then, as I mentioned earlier, this is determined by defect structure. So a particular crystal or a particular device that has been fabricated may be good for one application. It's the same semiconductor or the same junction or whatever, but it may be not good for the other application simply because the defect structure is such as to control and affect the lifetime that is there. I want to take up a brief venture into the idea of photoresponse time, or how does this semiconductor behave using these ideas that we've just developed of minority carrier and minority carrier lifetime. When we illuminate the semiconductor briefly for a short period of time and then turn off the light. So what happens to the minority carriers? How do they increase with time under that illumination? What happens to it as long as the light stays on? And then when the light is turned off, how do they recombine, or at what rate do they recombine? We can look at this for a moment. So we are going to use a step illumination, which I could show as a function of time being something like this. This is t. At t is equal to 0, we turn on the illumination. In other words, this is also a measure of the rate of generation. Okay? So it's a step function there. There's nothing before it. All of a sudden it's on. And then we turn it off at some time t off, where t off is greater than tau h. So it's gone past the minority carrier recombination lifetime. All right? So this is a measure of the G that is being used, the rate of generation of minority carriers. Now what we do is to make use of this equation that we just had to see how the rate of rise of the minority carriers will be. What we just had was d delta Pn by dt is equal to G pH minus delta Pn by tau h. Namely that the rate of increase is equal to the rate of generation minus the rate of recombination. We can integrate this equation keeping in mind that GPH is a constant over the time from when it is turned on. There is no change in the rate of generation. So GPH is a constant with time. And when we integrate this equation, we have natural log GPH minus delta Pn by tau h is equal to minus t by tau h plus some integration constant. Okay? You're integrating dPn and you got a delta Pn there, and you can do that. So dt by tau h, you get this equation. All right. Now we want to know what is the integration constant. So at t is equal to 0, what is the excess minority carriers that we have? In other words, what is delta Pn at t is equal to 0? What is it? 0. We just turned on the light. So delta Pn is equal to 0 at t is equal to 0. And using that, then we can solve for C1. C1 is equal to then ln GPH. So rewriting the above equation then in terms of delta Pn, okay, rewriting it after putting in C1, we can then write delta Pn as a function of time is given by tau h GPH times 1 minus exponential t by minus t by tau h. Okay? Put GPH there and rearrange this in terms of delta Pn. And now because we have it in terms of time, I express it as delta Pn as a function of time. So looking at this, we can say that the carrier concentration, the minority carrier concentration is going to increase exponentially with time, with a time constant equal to tau h. That's the implication of this equation. And at very large t's, what will happen when t is much, much greater than tau h? So we'll end up with some constant value. In other words, the excess minority carrier concentration will saturate in time. It does not go on indefinitely increasing. So at large t, or t, equal to infinity if you want, it doesn't have to go that far, beyond tau h somewhere increasing, we then end up with delta Pn t is equal to infinity is equal to tau h GPH. So far what we have can be sketched schematically, that I turn on the light at t is equal to 0, okay, and what is happening is that there is some minority carrier concentration. It is going to rise exponentially to some value, and then it saturates. Okay, so no matter how long I keep that light on, it's not going to go beyond that. It exponentially rises to some value. This was my original Pn naught, the equilibrium value for the minority carrier. Now it has gone, so that it is now Pn naught plus delta Pn. And this height here is what? what is it? Tau H GPH now, right? Because that's how it is it's the saturation value. So we can say this is tau H GPH. So we know this part of the diagram. Now we are also interested to know what happens now to this minority carrier concentration excess after the light is switched off. So beyond T off, which is this point, that's T0, and this is T off. Beyond this, how is this minority carrier concentration going to behave is the question. So what we'll do is, we'll take T dash is equal to T minus T off. In other words, beyond this, I'm introducing a variable T dash, which is measured with respect to T off. My starting point in that scale is T off. Okay? When the illumination is switched off, we have T off, the condition much greater than tau H. That was one of my assumptions to reach saturation to start with. Okay? At that point of time, delta Pn T off, or expressed in terms of T dash, it will be T dash is equal to 0, is simply the saturation value tau H GPH. So I'm going to start with this value on my scale of T dash and see how that decays with time. So this can be written then in terms of T dash. At T dash is equal to 0, which is the same as saying at T off in the time scale, we have tau H GPH. I can go back to the original equation that we had for the rate of change, namely d delta Pn by dt is equal to GPH minus delta Pn by tau H. And what we'll do is here, there's no more illumination. So what happens to that GPH term? Zero, right? Because I'm not generating any more of these excess minority carriers. So that's going to 0. And we can then solve for T dash greater than 0, which is equivalent to saying T greater than T off. Okay? I can make the substitution here for D. Remember, T is equal to, T dash is equal to T minus T off. So when we solve this, we can rewrite this then as delta Pn by dt is equal to minus by tau H. And we can make the substitution for dt in terms of dt dash. So when we do that, we get d delta Pn by delta Pn is equal to minus T dash by tau H. Yeah, I substitute, well, sorry, dt, very correct, dt dash by tau H, which now I can integrate to arrive at a fresh equation for what is happening after the light is turned off. So again, I want to know what is C1 or C2, let's say. And my condition there is that at T dash is equal to 0, delta Pn is equal to the saturation value, right? So I can make that substitution in there and solve for C2 tau H GPH. So my equation for the decay of the excess minority carriers after I switched off the illumination in terms of the T dash comes to be tau H GPH exponential minus tau T dash by tau H. Very similar equation to the other one, except that this is a decay, it's not increasing. So again, what we see is that the decay is an exponential decay with a time constant of tau H. In tau H, it will decay to 1 by E of its value. That's what's the implication of this. So I can go back now and finish up this sketch that we started here. that beyond T dash we will have then, I'll redraw that sketch. And what we had was that the minority carrier came, increased to some saturation value, and now it's just going to decay down exponentially to the same equilibrium value that it started off with. Okay. Remember, T dash is starting from this point. So on the T dash scale, which we have written for that equation, T dash begins from here, from T off. So this equation that we have in terms of T dash describes this behavior. Okay? So this is what we would expect when we illuminate a semiconductor of a particular type, N-type in this case, and watch how the minority carrier concentration increases, as we saw earlier, very drastically, some 10 to the power 12 times, and then over a time constant of tau h, it decays back to its equilibrium value. Now I want to take up another issue. It's unrelated in most ways, but it's still dealing with the semiconductors, namely diffusion and conductivity. You see, so far what we've been doing, we've talked about the influence of an electric field on the carriers in a semiconductor. I apply a field, the carriers' electrons will drift opposite to the field, and the holes will drift in the direction of the field. That's the current that we have, right? So what happens if we have a lot of something on one side, namely there is a concentration gradient. There's lots of something here, and there's less of something here. From what we already know, diffusion of that species will take from a concentration of higher concentration to that of a lower concentration. And not only is this true for atoms and other things, this is true for electrons and holes too. So in addition to my drift current, which is in response to an applied field, even in the absence of a drift current, even if there's no field, if I have a concentration gradient in the material, then I will expect the flow, say for electrons, from one end to the other, which constitutes a current. So even in the absence of an electric field, there will be current flow, right? So there's both of these aspects that are there. Obviously, we will see it comes to a point where the current flow will stop, but as soon as you do create a situation like this by whatever means, you can expect, in addition to the drift current, a contribution that is going to come from diffusion current. And that's what we're going to look. The laws that apply here, you're familiar with already. Fixed laws of diffusion, which simply expresses, say, the first law, that the flux of the species, when we use the word flux, we are talking of what? Something per unit area, per unit time. So the flux of the species, the number, is going to be proportional to the concentration gradient, the proportionality constant being the diffusion coefficient. And because the flux will be in the direction from the higher concentration to the lower concentration, there is a negative sign to indicate that. Okay? This is the basic fixed first law. And we'll make use of this, the diffusion coefficient, the concentration gradient, and the flux of the species to try to arrive at what will be the diffusion current if we have such a gradient in the electron concentration or in the hole concentration. We may write the flux, or let me write that, the flux of electrons in such a case can be expected to be equal to minus some diffusion coefficient term, which we write dE to indicate it's for electrons, times the concentration gradient of such a in such a sample. And you may wonder how such a sample is even created. I'll give a very simple example why there should be a concentration gradient. One of the easy ways of introducing a dopant into a crystal is simply, especially for crystals in which the particular species, the dopant, can diffuse fast, is to attach some solid which contains that dopant species to the silicon wafer and heat it up. And when you do, obviously there's a high concentration of whatever is in here and it starts diffusing in. At any given instant, obviously there's a lot more here compared with here, because it's diffusing in from one side only. And so when you stop that diffusional process, you arrive at a sample like what I'm talking of, with a concentration gradient on from one side to the other. And so when you look at such a sample, we got a concentration gradient, lots of electrons due to the donors on one side, fewer electrons on the other side. Now remember, excuse me, this is the flux. Flux is number of electrons per unit area per unit time. If I multiply that into electron charge, what do I get? This is the number of electrons. I multiplied it by the charge on each electron. What do I get then? Current density. Okay? So basically, this term multiplied by E should give me J, which is current density for the electron. So we can go to that and write, therefore, that the current density for the electrons, or the symbol we'll use is the diffusional current for the electron. So the current density is then simply given to us by minus, in the case of the electron, because the flow of electron is in one direction, current density is in the other, we have to multiply this by another minus. So in this case, it will become plus E dE dN by dx. We are now talking of actual current, not of electron flow, and that's why we are multiplying it by the negative sign there to account for that, right? So this is the diffusional current density in the presence of a concentration gradient dN by dx. So if we apply a field, we have drift current in such a sample, which follows the earlier rules that we had, and now in addition to that, you have a diffusional current. Similarly, for holes, we would have, because the hole current is in the same direction as you have for the flow of the holes, so the negative sign is retained there, dP by dx. Okay? So these define the two things, electron diffusional current due to electron motion across a gradient, and diffusion current due to hole motion across a gradient.
So when this value is significant enough for in comparison to drift current?
It can be in certain cases.
Because after a certain time, both the concentration of electrons
Yes.
both sides will be equal.
And it will stop. Yeah. So what will that we'll see what are the implications of that. Okay, when we come to that. You can think of a situation where it could play a very significant role in understanding, namely, imagine a p-n junction. Okay? On one side, I got lots of holes. One side, I've got lots of electrons. So as soon as I create a p-n junction, when we come to study it next, we'll make use of this idea. That something is going to happen. It won't go on flowing. We will establish some equilibrium.
In case of p-n junction, there will be diffusion formed.
That's exactly related to this, because there is a diffusional current. Now, it's not going to flow on and on in an open circuit, right? So if there is nothing to connect it, there's no reason why it should flow. But after some time, some equilibrium is established, which you already know from the basic ideas of p-n junction, which we'll take up again. So I'm not suggesting that this is a process that will go on just like a drift current in the presence of a field, but it does play a significant role in understanding the behavior of these materials, where we have a concentration gradient. And I'll show you a specific application. I'll tell you a specific application later. So now I can write the total electron current is both the drift current and the diffusional current will be given to us by our earlier expression for the drift current, which we obtained, sigma E where sigma is Ne mu E, plus this term that we have here, E dE dN by dx. This is the total electron current in the presence of an applied field if we have diffusional current also acting. Similarly, the whole current will be given by EP mu P epsilon x plus, in this case, sorry, minus E dP dP by dx. Okay? Now let's consider an example of a semiconductor. One side I have, on both sides I have evaporated 2 electrodes. You'll see where it is a practical example. One side, the electrode, the contact that I have evaporated is opaque. But I made it thin enough here, or I chose such a material. We have what are called transparent contacts, which both conduct as well as are transparent. So it's only partly opaque, so it's semi-transparent. And I hook this up to a source. It is an N-type semiconductor. So there is a certain distribution of electrons in here uniformly. So it's a uniformly doped semiconductor. You'll excuse me. And the field direction in the semiconductor is this way. We define x along this axis. Now what I do is, when I look at it, there is, in such a case, already there is a drift current because of the applied field from left to right. The electrons are moving in the opposite direction in response to the applied electric field. Now what we do is we illuminate this sample. Let me redraw that then. The same sample, keeping the field intact that I have applied, I illuminate it with light. This was the N-type sample. What's going to happen? It's exactly the same situation as before. My drift current is still from left to right. Electrons are moving from right to left. What else is happening here? I've illuminated it with light. Why? First of all, what will happen when the light falls on the sample? No, don't go to photoelectric effect. Electron hole pairs form. We just saw that, right? You shine light on something, I generate a lot of excess carriers compared to the equilibrium value. So what I'm doing now is I'm generating a lot of holes. Okay, I don't know how to show the holes. I'll just put some plus sign here. And in addition, I'm also generating excess electrons in this area. So now what is going to happen in the presence of this illumination? I can maintain the concentration gradient because the light is continuing to generate electron hole pairs, and now the diffusional current will flow. The electrons start moving this way. Holes also move this way because they are higher concentration here. So now we have hole current is this way, but the electron current is this way. This is the diffusional components of it. Whereas in the drift case, the drift current, electron current was this way. And the whole electron current was also this way. I'm sorry, not the whole electron current, whole current. There's nothing called in drift terms. So now we get that the drift current and the diffusional current for holes is in the same direction, but now we have that the drift current and the diffusional current for electron are in opposite directions. Okay? You can see, so this is, as somebody mentioned the word, the photoelectric word there, in some of those kind of devices where I'm not creating some artificially doped situation as we did here, excuse me, where I'm not able to maintain the gradient. Once it starts flowing and it establishes equilibrium, there is nothing more to it. But here we see that as long as the light is on, electron-hole pairs are getting generated, and in that case, these diffusional currents could be significant in determining the role. So our solar cell kind of behavior and all that, where light falls, in those kind of situations, we have to worry about both these currents, diffusional as well as the drift current. We have a relationship that I'll give, which are known as the Einstein relations, that relate the diffusion coefficient to mobility for both the electrons and the holes. You may wonder why they are related. When you think about it, mobility is a measure of the ease with which the electrons can move through the material under the influence of an applied field. Right? Diffusion coefficient is also a measure of the ease with which the electron or the hole can move through the material under an applied concentration gradient. So they are not completely dissimilar as we might think at first glance. They both refer to the ease with which the carriers can move in the semiconductor, albeit under different gradients. Einstein's relations are the following: dE by mu E is equal to kT by E for the electron. Excuse me. dH by mu H is equal to kT by E. So these two are known as Einstein relations. And what we see is that the diffusion coefficient in each case is proportional to mobility, and diffusion coefficient is proportional to temperature. The temperature part is very obvious to us as for other samples, but in addition, it is also proportional to mobility, because the same kind of things that cause scattering in mobility, namely defect structures, will also scatter the diffusional carriers. So this is an intuitive kind of thing that we can look at. All right. Just to briefly take up this idea of a built-in potential that will develop when we are talking of how long this diffusional current will last in the case where we have only that artificial concentration gradient, say by diffusion. So here we have a sample that as I said, we may have doped by diffusing in something from one end. And we are going to consider what happens to this sample immediately after we stop that diffusional process. So there's no more creation of those extra donors or acceptors, as the case may be. We will take the case of an N-type sample, and we say that there is a concentration gradient along X from one end to the other end. If that is X, we've got a lot more of something here, in this case electrons. Actually it's donors, which means electrons, because we've diffused in the donors. And then we've got a few of them. It is a gradient is there. So we are looking at this at the moment at which we stop the diffusional process, and then what's going to happen in this case. So N is equal to an X. There is a variation with X is what we say. To start with, the sample is electrically neutral. Okay? The electrons are there, so are their ionized cores. So the sample is not got charged up because I have diffused in some species. But as soon as I stopped the diffusion process, I will get a flow of electrons from this side to this side. So now in terms of its electrical neutrality, this side is getting more electrons and it's going to get negatively charged. I've also got now the creation of left behind positive cores more than there are electrons that were to keep it neutral. So this side is going to get positively charged. And this process will continue but then the diffusional current starts kicking in too. Because now on this side I'm having too many electrons and so on. I'm sorry, the drift current will start kicking in. Here I had the diffusional current causing this behavior, but after some time now what I'm getting is some kind of a potential where I've got plus here and minus here. So under this influence, the electrons are going to migrate this way in response to the potential. So in the doped sample, diffusional current starting to flow this way, or the electrons starting to flow this way, leaving behind positively charged cores here, and so now we have a applied electric, a built-in electric field that is getting there, because now I've got lots of these positively charged cores left behind on one side and excess electrons on the other side. So after some time, these two processes will come to be in equilibrium. And what we are interested in is to evaluate, under that equilibrium field that is established, what will be the potential difference between 2 points where the concentration is, say, N1 and N2. Okay, so now there is a potential field that has been established. It's come to equilibrium between the diffusional side of it and the drift side of it. And we want to know that at a point where along X, where the concentration is N1 and N2, what is the potential there, namely V1 and V2 is what we want to evaluate. At equilibrium, after all this has happened, the total current density, JE, is equal to 0. Which means we can write then that En mu E times the field, which is the drift part of it, plus E dE dN by dx is equal to 0. I can substitute for the field here as minus dV by dx. And so we can then write E n mu E dV by dx, the minus sign, is equal to minus E dE dN by dx. I've simply taken it on to the other side, so you get the extra minus here. And if we simplify this out, we'll get that dV by dx the two minus signs also cancel out. So dV by dx is equal to dE by mu E 1 by N dN by dx. What is dE by mu E? We just saw Einstein's relation. So I can write that as kT by E dN, and this dx terms go, so dN by N. All right? So I simply get dV is equal to kT by E dN by N, which I can then integrate from N1 to N2 dN by N to determine what will be the potentials at positions where the concentration gradients, concentrations are N1 and N2. So we'll then get up that V2 minus V1 is equal to kT by E, the natural log of N2 by N1. In other words, the potential difference between these 2 points is proportional to these values. What is the concentration gradient? So depending on how strong is the gradient, depending on the points where we are considering, the farther apart these points are, the more is the gradient between them, because this side had a large gradient to start with. So delta V depends on N2 and N1 from this equation. What we can also do is, if we know the dopant concentration profile, in other words, what I simply said that N is equal to Nx, if I knew what this profile looked like, I could evaluate the gradient. Let's suppose that we have an expression that Nx is equal to it's equal to ndx, again we are assuming complete ionization, is equal to some distribution that looks like this, n naught exponential minus x by b. This is related to how it has diffused in. So given this, now we'll go about evaluating the field that has been built in. I would need to know a dn by dx2. So I have to differentiate this. Okay. Am I right in that? dn by dx is equal to minus n naught. Okay. And again we start with our equation of the total JE. I have a drift component, I have a diffusional component. JE is again equal to 0, so I have the same equation En mu E x, except this time I'm not going to substitute for minus dV by dx there, plus E dE dN by dx is equal to 0. So what I'll do here is to make a substitution for this, and again 2 e's will cancel off. Then I have kt dE by mu E, again expressed in terms of kt by q. So when we do that, we have epsilon x times, or the field times n, which was n naught by b, no, n naught exponential minus x by b, will be equal to minus dE by mu E n naught by b exponential minus x by b. Simply substituting there. And here then you can substitute for kt by q. Actually the minus is going to come, 1 minus we have there, so that will be a plus when we took it to the other side. Right? So we get this expression here, we substitute for kt by q, all these terms are disappearing, and what do we end up getting? The field then is equal to dE by mu E times b, or kt by be. Okay? So this is the built-in gradient, the built-in potential into that sample due to the presence of an initial doping variation between one end and the other. It has reached equilibrium, and so now nothing is flowing, there are no currents flowing through it, but there is a built-in potential in the sample. Now what that has a role to play is, say for example in a transistor, the base is doped non-uniformly. I think we'll come to this again when we come to the devices. And by artificially doping the base non-uniformly, we create such a built-in gradient. And we will see that what it does is to speed up the flow of carriers through it. Because in addition to the applied fields, there is this built-in potential too that aids that process. So it makes the transistor faster because of this action of a built-in potential being developed in it. So it's not simply an academic, it's got a nice application also there. Just to bring this part of it, since we are dealing with light, to a close, a few terms related to the emission of light from semiconductors and the production of light, which I've dealt with that more in length in the course on photonics, but I will just briefly, for the sake of those who may not have been there, run through this very quickly. Just a few definitions. Luminescence is essentially the emission of light by the electron-hole recombination. Incandescence, on the other hand, is the emission of light from a heated object. of radiation, which includes light, from a heated object. And as you can see, our light bulb, the ordinary bulb, is an incandescent bulb, but an LED is a luminescent device. Okay, the distinction you see there. Very quickly, depending on the exciting source, we will call it photoluminescence, if light is the thing that excites and causes the luminescence. We will call it cathodoluminescence if it's electrons that are striking in a vacuum and exciting, that the energy is being produced for the electron hole pair creation due to the electron striking the target or the material in a vacuum. Example, your cathode ray tube. Okay? And then we have electroluminescence, when a field, a potential gradient is used to excite and create the electron hole pairs. Example are LEDs and so on. Photoluminescence, cathodoluminescence, and electroluminescence, depending on how we have passed on the excitations. I think I'll stop there. Just by way of saying, there are two words you may remember: fluorescence and phosphorescence. In one case, fluorescence, the light that is emitted, the luminescence lasts for a very short period, nanoseconds maybe. And in the case of phosphorescence, it could last for hours. We won't go into the mechanisms behind it, but these are, so in this case, it's a very short duration emission. Here it is a longer duration. Okay? I'll stop with that. Do you remember how a tube light works?